Hi, everyone. Welcome to the panel number 3, measurement and data. So as we have seen over the last few days, thank you. We will be focusing today on measurements, especially where the above ground clutter is involved. We have seen in the previous sessions that modeling the excess path losses due to clutter is difficult. And measurements will be very important in this. So regardless of the models that we will arrive, whether those will be based on deterministic analytical models or based on empirical statistical models, a lot of measurement data will be needed in order to either validate or confirm the models or to train empirical and statistical models. So measurements are quite critical in these aspects. So the discussions today in this panel, we will deal with how to obtain such measurements at scale and how to process when we have the measurements in order to make the best use of them. So today we have a great group of panelists. All right. So I have Dr. Barak Berskoy, which is Director of RF Engineering at NetScout. We have Dr. Julius Faugian, which is expert member of the technical staff at AT&T. We have Max Hollingsworth with ITS, which is soon to obtain his PhD at the University of Colorado. And then we have Dr. Frank Lind, researcher at MIT's Haystack Observatory. And myself, I'm Adrian Florea. I'm Director of Data Science at Communication Research Center in Canada. Right. So today, what we're going to cover at high level, we're going to go first covering what are the specific related to clutter loss measurements and what's specific about that, what are the unique things that one will have to do in order to make relevant measurements there. Then we're going to talk about, once we have the measurements data sets, how we can use them most effectively. We're going to look in some aspects and particularities of geodata, which is related to such measurements and the limitations and the constraints and how to use them. And then towards the end, we're going to go in perhaps some more contentious topics. How can we better share measurement data, which is not an easy thing. And also, we have a couple of the points of discussions that happened earlier this week and also last week at the study group 3. People have been discussing on the impact of directive antennas in the presence of clutter and multipath, and what is the impact and how that can be modeled for sharing studies. That is an open discussion, and we're going to touch base on that. Is that something we have to look from a measurement point of view? All right, so let's go into it. So for the first topic on clutter loss measurements, we have talked in previous days, including in the fireside chat this morning, about the challenges on building consensus on clutter. So in any consensus building process, it will be easier, it will be facilitating things if the process can start from a set of agreed facts that everyone can agree with, objective facts. Could propagation measurements serve as an objective foundation towards building consensus on clutter modeling? Julius, may I ask you?
Yeah, sure. Yeah, so where I can start with is that there are many use cases of propagation models, and some of them are being used for interference analysis that we've talked about previously. Some of them are being used by service operators to determine the service areas and also to gauge or predict quality of experience for the customers. Then, even within those areas, there are different categories of application of the propagation models. But one of the things we know, regardless of the use case, is that everyone is striving to have accurate propagation models that more or less mimic what they're trying to, what they'll have in the field. So with that in mind, if we are looking at what we are going to predict, say through a propagation model that aligns with what is going to be measured in the field, then it means that measurement data needs to come in either in the form of being used to calibrate the propagation models or being used to validate the propagation models. But at least the foundation for what everybody is striving for, and I think that everybody agrees with, is that accurate modeling is needed. Now, we also know that there are different types of propagation models in existence. Some propagation models are more suited for one use case, the others are suited for some other use cases. But at the end of the day, in order to achieve that accuracy in terms of propagation models that comes closely to what is being measured in the field, it costs a lot of money for some organizations. For example, in the case of AT&T, it costs tens of millions of dollars to have propagation models that are accurate, because we are interested not only in determining signal level, we are also interested in more or less, even within our own network, to see where some of the sites interfere with other areas. Because at the end of the day, if the models are not accurate, then it can be extremely costly. For example, if we're under predicting, then we can build a lot of sites that will cost additional hundreds of millions of dollars that are really not needed. And again, you build in the wrong place, you have too much overlap. Again, it's self-interference, so you are spending when you are not getting the quality. So that's why it's really important for us to look at how the propagation model behaves right from the transmitter to the receivers. And when we are talking about the receivers, one of the use cases is where our customers are, and our customers are located everywhere across the geography. So now with that in mind, looking at everything as accurate as it could be, then it goes into the type of propagation model that we choose to use, which requires different input. So yeah, so we also have the situation where even with, say, measurements data that we are talking about, there are different types of measurement data to fit different aspects of the end-to-end process. For example, we may be building a new carrier on a frequency band that had not been deployed before. So that way, we don't have network data to utilize to gauge how the network looks like. So we rely a lot on, say, CW drive tests, and we are talking about nationwide, which is quite a lot, to calibrate propagation models that are applied to predict how signal would go. So, but then as we come into the specifics on how the models are calibrated, that's where it gets into a whole different level, because we may have measurement data, but it needs to be good measurement data. So the quality of the measurement data is important. Then the models that we calibrate and how we apply them is important, because we may calibrate a model in one location, but you go to the next area, that model, despite the fact that it's calibrated and valid, is completely not valid for use in an area where it was not calibrated to be used in. So that's why we take a lot of emphasis into how the models are calibrated and how they are applied for the specific frequency band and our mode of deployment. Is it above clutter or below clutter, the type of radio and all the like. So yeah, I'll wait there for now.
Thank you. So I gather from your comments that you have to ensure a comprehensive diversity of measurements to cover all the situation, all the use cases, in order to cover all the angles and all the possible situations for calibration. And also, it's very interesting you described that, how it works for internally, where AT&T. But I guess similarly, when you are in a sharing situation with someone else and you want the common methodology or common approach in order to have an engineering analysis, it has to cover all the angles and all the diversity of environments and conditions in order to be comprehensive from the perspective.
That's correct.
Yeah,
so
yeah.
We work with other operators, we work with other users. The first thing is, even when any analysis needs to be done, we need to make sure that it's accurate, right? So that's why we go into the assumptions of what is needed, how it's being done. And in all of this, one of the key things is none of our propagation models can be accepted, which does not incorporate the right geodata set, the most up-to-date geodata set, and includes clutter. And here we're not just talking about clutter classes or whatever the case may be. Clutter heights is critical because there were times back in the day, many, I would say more than 10, about 10, 15 years ago, where we used to look at things like clutter classes and apply statistical heights that are derived and calibrate models on that. But the level of accuracy that we got were not as good as when we're using clutter heights information. So that's why whenever we talk about clutter, we always incorporate not just the clutter classes, the clutter heights go hand in hand on a bin by bin level.
Okay, thank you. So considering that, so the use case of interest is key, okay, when you conduct the measurement. So now let's go back to the main use case of interest, or maybe too general, okay? In the case of estimation of clutter losses, you want to do some measurements specifically for that. What will be some specific things to consider for measurement? Or you want to comment on that?
Sure. So just as a bit of a background, I'm with Newfield, and what we do is my group, we collect CW measurements with the specific purpose of calibrating, tuning propagation models. So, and we've done more than 50,000 CW measurements in various locations, various frequencies, with each having more than 1 million sort of raw measurements. So I think I'm qualified to answer the question, at least. So I think it comes down to 3 things as far as collecting good data in general goes. One is the area of equipment selection and care. The other one is the location selection and the drive route selection for the test itself. And the third is, what you do during the test to ensure quality. So at the end of the day, yes, you do need some quantity of data to ensure stability of the models and making sure that you get a good, valid parameters calibrated. But once you reach that enough data points, then you get diminishing returns in each additional quantity of data that you get. What's more important, in my opinion, is the quality of the data that you collect, because there's so many things that can go wrong during a measurement campaign. So I'm going to go back to equipment selection, for instance. One, we want to select all of the equipment that we use to minimize the uncertainty of the measurements that we collect. And that means selecting transmitters that don't have a frequency shifts, for instance. You can have frequency shifts with temperature in various equipments. We test in 115 degrees on a rooftop in Dallas sometimes, and you want to make sure that the transmitter can handle that. And we also test all of our equipment, particularly antennas, in the open test ranges to make sure that the patterns and the gains that are claimed in the data sheets are indeed what we observe when we use it in the real world environment. Of course, we test the cables and whatnot as well. But one of the keys, I think, in our process is, and this was kind of said to me on day one when I first joined the company, and it's been preached all over and over, is you have to handle the RF equipment as one of those fine wine glasses. And I mean, you know what I'm talking about, the ones that you put in the dishwasher and it comes out broken. So that you have to use, you have to use RF equipment. You have to treat that the same way. So that's on the equipment side, and of course you want to make sure you have the highest dynamic range possible in the receiver selections that you have and whatnot. On the location selection, we typically do area-based models. As Julius mentioned, we want to model a particular area and customize our propagation model to work really well in that area. And I've a lot of the conversations that has happened here so far, they talked about more general models that can handle a variety of different situations. We take a different approach, and we're trying to do more customization on a given area. So we want to make sure within that area we have a good geographic distribution of the locations that we test. We want to make sure we have some sort of a height distribution among the locations that we test as well, because in the models that we use, effective antenna heights is a consideration. And we also, of course, when we talk about clutter losses, we want to make sure we have a good diversity of clutter losses, primarily for the predominant classes that we're trying to model for in the area. But we also don't want to skip over the clutter classes that are maybe not so frequently appearing in the area. So we have to select the locations that way. And finally, in the test itself, I talked about maximizing the dynamic range. We distribute the samples. We want to make sure we get a good amount of samples close in the mid-range and far away from the transmitter. And it's not so easy because close to the site, you don't have a whole lot of area that you can test close to the transmitter. And far away, your signal dies, so you don't, you can't get as much signal. So we want to normalize that in order to not bias the data from one way or another. We do monitor the interference, for instance. I think that's really important. Like, when you do a CW measurement, you monitor the channel that you're trying to measure, of course, but we also measure some adjacent channels, empty channels that aren't supposed to have any transmissions. And then if we do pick up any type of transmissions or higher signal levels in that means that there's some sort of a interference in the area, and we discard those measurements. So, and we also, finally, I think, there is a redundancy in the test that we do. I think that's really important, whether it's collecting simultaneously multiple frequencies, that ensures that if, we know about the theoretical and practical differences that should exist between two frequencies, if that's not holding true throughout the test, there's reason to believe that there was some sort of an issue with equipment or the way that the test was collected. And, one of the other ways is to we put a couple of different teams that are testing together and test the same frequency, the same signal, and see if they get the same. So those are some of the kind of practices that we developed over the years in order to collect not only quality data, but also, in higher volumes.
Any considerations on the reception antenna height? Most of these tests are drive tests?
Yeah, most of the work that we do are drive tests. We do have, it's typically on top of the car or SUV, whatever we use. We did have some projects in the past where we've collected in a little bit higher heights. It was more for the FWLL use cases, and but you do have a limitation. You can't drive around with anything more than, I believe, 12 feet over sticking out of the car. So we have to work within that range.
Thank you. All right, so based on all this, evidently measurements will be expensive, okay? And then they are never enough, okay? Short supply. So my next question goes on to, if we have, can useful information be extracted from measurements or measurement data which does not exactly fit the use case of interest? Okay? So we need some measurement data to validate the model. There's not enough minor resources go to conduct an ideal measurement, but to have some other data collected maybe close enough, but not quite exactly what we need. Can such information still be useful and take it advantage of in order to be processed? Okay. And in that train of thought, could someone think about the generic measurement setup that we could design, and then that measurement setup, more generic, would support a broader range of use cases, rather than every single time we do a measurement geared specifically to a specific use case and you cannot really use it for something else. Max, you want to comment on that?
Yeah. I guess in terms of shareability, I think at ITS we do a lot of measurements with something in mind, right? A use case in mind. And then when it comes to shareability, that we hang on to those measurements for a long time. And the thing that makes them, I guess, most useful or best for sharing is if you save everything from the rawest measurement all the way up to the sort of final product. And for example, with the mid-band data set that's going to come out next month with millions of measurements in it. There's probably 4.5, 5 steps of processing from the raw measurement data to the actual DB JSON files that you're going to be able to download. But if you're trying to reuse things and you're trying to reuse stuff for perhaps a different possibility, you got to have access to the lower level processing. I mean, we remove things like terrain data because we're just looking at clutter. And so if we just release the clutter data, there might have been a lot more useful things in those lower steps of the processing chain. And then in terms of a generic measurement setup, I'd say the best thing you can do for that is to try and remove as much from the measurement taker as possible. So if you can use a signal of opportunity, do it, because that takes out a lot of complex parts of a measurement system. You're trying to synchronize the transmit system with the receive system. If the receive system can have GPS and the RF signal measurement combined, then you've already taken away a lot of the trouble that a user would have to go through in creating a new measurement set. Yeah, I think that's my thoughts.
So ITS, you will be sharing the process data, not the raw data. It's not going to be part of what you're going to share, right?
Right. Yeah, it'll just be the processed one. But I think there needs to be this mentality shift of.
I think I have a question later on something.
Yeah,
related to that.
sure.
Yes, that's good. Okay, so you mentioned about the equipment characteristics tolerances, temperature drifts, and stuff like that. So there's a lot of uncertainties that can play into a measurement process, and that affects the end results. How can we handle this? Max was just saying earlier, so do the full details about the measurement setup, the equipment characteristics need to be attached to measurement data in order to make use of it. How can we get to handle that and to understand the uncertainties in the measurement data and characterize? Okay. Frank?
Okay, I actually think it's worse than that, because a lot of systems have implicit information associated with them. Sometimes it's in the heads of the engineers. Well, what cables did I use to hook
Biases,
stuff up?
yeah.
How did I actually position that antenna in the field? Then there's software. Today, it's all software radios at the back ends of a lot of measurement systems. I know at Haystack, we build a whole range of scientific systems, and the back ends, honestly, have over the last 3 decades gone from being incredibly specialized to completely convergent, architecturally, performance-wise. Sometimes we're pushing terabytes, petabytes of data around very often for experiments. Underneath dealing with that complexity, you actually have to have these signal processing and analysis chains that are in software and firmware, revision controlled, archived, characterized, available at some level. And there, various, if you're using open equipment, that's fairly straightforward. But if you're using, Keysight's latest spectral analyzer, they probably have a lot of algorithms that they're not really wanting to put out on the internet for everyone to copy. So you get into, well, what was the instrument transfer function actually?
Oh.
And one of the ways around this that you can do is to fully integrate calibration systems and architectures and experiments into experiment execution. So we always, when we build systems, we integrate calibration from the start as early in the process as we can. Very often instrumentation that's deployed for various purposes and measurements does that. And then, whenever possible, we keep IQ. Now, we can't do that at very wide bandwidths for very long times often. We do extraordinarily well. I mean, for our astronomy systems, we're typically recording, 816 gigahertz for weeks and utilizing the IQ to do the signal processing. That IQ data is really the fundamental data, though, and it can be reprocessed. So it's as you go up the hierarchy of data in reduction for specific purposes, that there's low-level data at every intermediate stage. And the lower the level of the data and the more metadata about its collection and environment you can collect, the better you can do for repurposing data. It's very generic in general. The space sciences and geosciences have been doing this for a long time. NASA talks about levels of data product that you provide to various end users. And the lower you can push that, the more powerful it is. And I'll give you a very interesting example. global positioning systems, GNSS, or navigation satellite systems, as we call them now. The high precision receivers put out a carrier phase measurement at a low level of the signal frequency phase difference between, say, L1 and L2. So between the two carrier frequencies that were early on are now L1, L2, L5. There's multiple frequencies off these satellites. That carrier phase difference was only really in there because the geodetic systems really needed to correct for the ionosphere. We actually at Haystack scrape 6,000 receivers a day at a hertz or better from across the Earth. And we can take that low-level data product, analyze it for what the ionosphere is, and produce maps of the space environment, all right, that are incredible. And this only happened because that lower-level intermediate data product, and that's not even the IQ level, that's a carrier phase measurement, was available. And it was made available by a standard, all right? So there's a RINEX standard that said, you do this, precision things do this. Well, now everyone's phone is starting to get multi-carrier, multi-frequency GNSS in it. And there's the question of what's going to happen when we go from 6,000 sensors to 6 million or 60 million sensors. I mean, not everybody's going to opt in, but so this is where standards for data and standards for lower level data, along with integrated calibration approaches, can address some of these things. And it really is, when you step back, you look at why are you doing clutter models? You're doing clutter models because you can't oversample the structural complexity of the environment with measurements, and when you're in a given location, you don't instantaneously know between you and a given base station, between you and another mobile device. You don't really know the physical details to the level of ray tracing everything out and knowing every material. So you do it statistically as a fallback for not being able to oversample. And that gets you ranges and variances, and you can design systems with it. You can say, ooh, dynamic range. I need extra gain control for this region because. And so you put a particular terminal or antenna there to handle that. Or there's a mountain over there and I don't want to see the multipath off that. I need to make sure that that's minimized. Now, as we go to a world of spectrum sharing, all of a sudden, this kind of information and clutter modeling probably won't be good enough by itself. And height is one aspect of it. Making clutter models truly three-dimensional is challenging, as we've heard, from a measurement point of view. But the difficulty you have is now you have to make spatial decisions in addition to temporal decisions about things like, well, which frequency do I operate in to get out of the way of another signal that has priority over me? In some sort of dynamic spectrum sharing. Or there's been a request by a radio observatory that we're interfering with them. Could we please try not to? But it's done through a zone management system, for example. So it's happening on short timescales. And this leads to what I think in looking at kind of, I'm coming from a scientific look at this into Spectrum X, looking at research projects to go make measurements of various types. But I look at the longer term vision of this is, what does spectrum management of the future look like? And it looks like the Weather Service, but for spectrum, all right? There's going to be a lot of different models. You saw I don't know how many, I didn't count them on that page. There were different models for different purposes. But underneath, why are they assimilating data into a lot of their models? Well, they're doing it because, down in each of those models at some resolution cell, they go, well, crap, we can't model what's underneath this anymore. We're going to have an empirical model or a statistical model or a physics-based thing. And the models all fall back to those things when they don't have data. But when they do have data, it pulls the variances in and tells you in your clutter model, where are you operating, for example. And that's incredibly powerful for getting really accurate measurements out of systems. So I think that's the direction all of this ultimately needs to go. And it becomes dynamic the moment you get into a dynamically spectrum shared environment. It's very, very challenging.
So stepping back to more generic measurements, okay, for clutter characterization. So I understand from what you're saying, Berkeley, is that it will be quite a significant value to standardize how those measurements are reported, the metadata related to the characteristics of the equipment, all the setup of the measurements, any possible biases, antenna positioning, and so forth.
Yeah,
so
it's the information content.
So that will be the underlining data layer that will support the multitude of models that you want to build later on of that.
Yeah, and it gets more complicated as you make antennas more complicated as we go up to millimeter waves. It often simply doesn't make sense to have a simple monopole or dipole sensor or something like that. Additionally, a lot of times you need enough collecting aperture and sensitivity in a system that you're really over measuring to build your model relative to what a real world system would actually experience. And that's so you know the boundaries at low signal levels, at low clutter, at high dynamic ranges that your phone might experience as, oh, I'm not really working as well as I wanted to. But your dynamic measurement system actually has to be able to resolve a lot of that.
Okay. So all this obviously sounds complex, expensive, not easy to get. So reducing unknowns and uncertainties can be done with significant effort and cost. Crowdsourced measurement data was mentioned a few times earlier this week at this conference. So that is obviously at the other range of the quality of measurements, also on the cost side. Okay, so it's low cost, is widely available, millions of data points measurements, also extremely noisy, poor quality, less control. So the question on that, is there a way to use that data, which is fairly available? We at CRC, we have quite a bit of it. In fact, there are data aggregators that are selling it. Can that data being used systematically in order to effectively tune or calibrate models, including clutter loss models? Is that something that could be considered as an alternative to doing the expensive and very high quality measurements? Max, comment on that.
Yeah, well, so at ITS we have the top tier, or our top tier sort of propagation measurement system is a CW system, and my work there has been evaluating and trying to provide accuracy guarantees for low cost measurement systems, and how do they stack up against that higher tier measurement system. And so I've looked at trying to provide accuracy guarantees to SDRs and to mobile phones. And what we found is, it's generally assumed that mobile phones have, plus or minus 8, plus or minus 10 dB absolute accuracy when they're measuring reference signals.
That's just the phone in itself.
That's just the phone.
Forget about that. It's in my pocket, or I keep it in my hand, or not. Okay.
Yeah. So, well, I can talk to you about the interference from your body and what we see with that. But just for the phone, what kind of guarantee can we give to that? And it's really hard to evaluate an individual measurement. It's hard to measure at the exact same time with the same antenna or whatever. But over time, we see that in general, each phone has its own sort of systematic error. And if you have a lot of phones, like you would in a crowdsourced measurement data set, and they're different models and they have different chipset manufacturers, then if you look at the mean measurement coming from those phones in a given area, you just need one measurement from 8 phones in sort of a 3 meter by 3 meter area. And you drive that inaccuracy from plus or minus 10 dB down to plus or minus 3 dB, because their systematic errors are kind of distributed normally around 0. Okay. And the more measurements you have from more phones, the better you can drive that. Of course, there's diminishing returns for the more measurements you make. It won't keep going down. But so there, we have sort of a positive or a general good outlook on what could we do with crowdsourced data if we were handed a lot of it. I don't know if you want me to talk about the body and the impact of that, but obviously these things make it more complicated. There's all sorts of things that make it more complicated, but for the device itself, they are calibrated instruments. Qualcomm has a calibrated chipset in those phones. May
I comment on this one as well?
Yeah,
we've actually done some investigation on this topic as well. And I think, that's one of the biggest challenges. And it looks like Max was able to, somehow diminish that challenge to a certain degree. What we've seen is also two additional, perhaps, main technical challenges and one business challenge, perhaps. The technical challenges with the geolocation accuracy of what's being reported from the phones. At the end of the day, the crowdsourced data, you don't necessarily know whether they're inside a building, inside a car, inside or outside, or, you don't, perhaps orientation doesn't matter if you're able to reduce that to plus or minus 3 dBs. That's not such a big concern. But you really don't know what environment the measurement is coming from. That's a big challenge. The other challenge is just the way that these measurements come back to the network is, phone measurements are limited by, the dynamic range is limited by the signal to noise ratio. And by definition, when you go far away from the site or from the serving cell, and you come into the coverage of a different serving cell, your signal to noise ratio drops. So as a result, a lot of the measurement that you get from crowdsourced sources is concentrated close to the transmitter itself.
So
And
you are far from the tower. The SNR for the neighboring sites will impact your measurements.
yeah, you don't necessarily get measurements when you're in the coverage area of a different
Yeah.
cell, right? So you're kind of restricted to the cell serving area, and if you don't have measurements from outside of the serving area, and we discussed a lot about the interference and whatnot, so that becomes a bit challenging to model the interference environment. And the third challenge, I think Julius talked about, is one of the main use cases in the industry for the models is when there's a new frequency allocated, when there's a carrier addition or so, and you want to know what's the impact of the new frequency, how will the coverage look like, and you simply don't have those measurements at that frequency. So
Very quickly.
For sure.
Uh,
Yeah.
Yeah, with the crowdsourced data as well, we've seen it a lot, and we have a lot of them. So one of the things is the layer management configuration in the network at that particular moment in time affects what data is seen by the user at any particular moment in time. So let's take, for example, something like the access threshold may be changed in the system for whatever reason, for different carriers differently. Then that will impact where you may see reported signal level from, say, the customer. And when you take that without understanding the other back end of what was configured at that moment in time to line that up with the crowdsourced data, then it makes it a challenge to align things and come to a proper conclusion.
I have a really
If I just 1 second on Julius' comment. So if I understand correctly, you would need to fully understand the network site configuration in order to make good use of the crowdsourced measurement. You cannot just collect the data that the phones report and then say, oh, this is what I...
Yeah, basically you can use the crowdsourced data to see how coverage looks like, how signal looks like. But depending on how you want to use the data, if you are talking about calibrating propagation models, except you are in a system where you are calibrating every single day based on data that you saw the previous day, then it makes it slightly more challenging.
Yeah, there are a couple things you can do with crowdsourced data to improve what you do with it. One is to have calibrated reference sensors that you use to tie in. There may be sparsely distributed in a region that you use to tie in measurements into measurement regions that then allow you to understand, for example, well, the typical outdoor signal level in this region is actually much higher than that cell phone. Therefore, it's likely in a building, for example. Another aspect of it is you can build models that explicitly solve for the biases as part of the model data assimilation. So you can put the bias into the overall assimilative framework, bring the data in, fit for it also, and then within variances what's consistent and what the biases of particular receivers are. And so you can actually do this at the receiver level and understand, well, that one's crappy, throw it out, for example, to get rid of it as an outlier. So there's things you can do to improve this process, but it is actually a different type of clutter model, for example, than has been constructed typically.
All right, thank you. So before moving to the next topic on the data sets, are there any questions? Maybe take
Hi. So we started the conversation by talking about CW measurements, and then we jumped to crowdsource measurements, predominantly using cell phones. Of course, the cell phone signal is a wideband instrument and not a CW instrument. You guys want to talk at all about the impact of that difference on the models and maybe where the line between a channel model and a propagation model is?
I can start. So we've done simultaneous LTE transmissions with a CW signal just sort of offset by 10 megahertz. We have a 10 megahertz LTE transmission, offset 10 megahertz CW signal. sharing the same transmit antenna. And then on the receive side, we're doing mobile measurement. We've got the prime measurement system that ITS has measuring the CW signal in its output. And then we have, if you guys have heard of it, SRS UE outputting RSRP, which is the power of the reference signals coming from the LTE signal. And because with the CW measurement system, we average over time while moving, we're getting an average over space and for the CW signal. And for the RSRP, which is coming from the LTE, that's an average over frequency and then also an average over space. We see basically perfect correlation or whatever between the two. So like mean absolute error of like 0.1, 0.2, 0.2 dB between the two signals. So it depends on what averaging you're doing, I guess, with the CW signal. But if you're averaging over space and you're doing a moving measurement, you get basically a perfect agreement.
My name is, I was told I had to reintroduce myself. I'm Tony Rainier, and I'm affiliated with various agencies doing clutter models. One of the challenges that I come up with, and I don't think I heard it from any of you yet. We go out and make a bunch of measurements, and you mentioned drive testing and fixed antenna heights. And yesterday, somebody suggested that if we could put cell towers in the middle of intersections, that was the best location for them. But ironically, that's where we make our clutter measurements from, because we drive our vans around with 10-meter heights and whatever. And so there's all this measurement bias that comes in these data sets. And we know this in advance. And most of it is unavoidable. But I guess my questions for you guys are, when you go out to make measurements, are there any techniques or anything that you typically do to try to sort of in advance at least explore the boundaries of those biases so that they can be published with your data and give people more information about how to use them? Thank you.
So just to make sure I understood that is the question. Is the interest here maybe think that the use case that most of the measurements on drive tests are done are geared towards lower receive antenna heights, and maybe there's an interest for other type of scenarios when I have maybe the receiver point is a tower with some, I don't know, 5-10 meter antenna. Is that what you're talking about? Yeah.
And I'm the modeler. Who knows what I'm coming at it with, but almost certainly I'm not coming at wanting to know clutter in the middle of streets in urban areas, kind of a thing.
Yeah. I think that's a great question. I alluded myself when I asked you about the receive antenna heights. And I know some of the models, they have corrections for the receive antenna height and you can apply it, but those have to be validated as well. Okay. So, yeah.
I mean, we do testing in quite a large variety of heights. I mean, we do it from anything from 15 feet to 300 feet. So, and we do it at various locations, including some intersections as well. And yes, you do have unexpected line of sight scenarios that you may not necessarily see in other types of environments. But these are also sometimes real scenarios that are happening. There are deployments on a lot of light poles and in the small cell scenarios now, and they're located in the intersections, traffic lights and things like that. So what we do see is quite a bit of distinction between the below clutter and above clutter scenarios. In fact, the models have that we use have a factor or parameter that can handle the variation of the transmitter heights. But there is the first diffraction. There's another phenomenon that comes into play when you're dealing with the below clutter scenarios, and it's not a clear cut, if you're below 20 feet, use this, or 25 feet, use this. It really depends on where you are and what environment you are. You can be below clutter at 40 feet in downtown Manhattan, you'll certainly be below clutter. But if you go to a suburban area at 40 feet, you'll be above clutter. So, but we do see quite a bit of distinction between the two, and from a modeling perspective, we typically model those scenarios in two different models.
So there exist measurements where both ends of the path are above clutter. I think that's what the point of the question.
Both measurements being the receiver being at about in a higher height
Yeah.
is a very impractical sort of approach in my mind. It has to be done at certain points. You need to know what that is, but you get such few measurements. If you think about a day, let's say 8 hours, if you can get millions of data points driving around, and if you're doing above some sort of a drivable height, you have to stop, you have to hoist the antennas up, and you take one measurement, you go to the next point. Maybe you're lucky if you get 50 measurements in a given day. So it becomes quite a bit of a challenge from logistics perspective. We do it in time to time. We do these multiple height measurements to see the effect of it, but it's nowhere near the large campaigns that we do for ground level measurements.
I think that this comes down to oversampling the ground level variability a bit and being able to characterize where you are in your statistical distribution in a given clutter model. Is that if you really could measure it, I think in our geosciences community, we call it mealtime. We call it measure everything all the time, right? So if you could really go do that, then that would be great. You could get very good statistics in different regions and understand where the boundary layers are. And I think that there's a limit for any given model to how much you can do that, just because the factors you said, logistically, this is very challenging. And I think as we get more complex environments, drones flying around above cities and aircraft, that are communicating to cell phones or whatever, spacecraft to cell phones, you're ending up with clutter environments and questions we haven't had to address yet that may care about this kind of thing. And so understanding where you are, for example, relative to the center of a street versus the edge of the street may become something that becomes more relevant. And, it's very challenging. It's where you get into, can you have things that help guide the models and help you understand where is a given system operating? What regime is it really in?
Thank you. Any question? All right, so there's one more. Sorry,
take one more?
Oh, sorry.
Okay, and also remind the audience tuning in virtually, please feel free to put your questions in the chat box, and we will try to get to those as well if we.
Thank you, panelists. Great session. I really enjoyed it. Eric Hill from ITS again. And earlier you discussed data from transmit. And
Sorry, I think the mic is not working.
It's like fading in and out.
Yeah.
sorry, can you hear? Oh,
Yeah.
there we go. Real great panel, the discussion. Thank you very much. And I had a question in particular about data alignment with transmitters and receivers and such. In particular, should GPS time or UTC time be used for data alignment, and why? I know the right answer. I need to convince others of the right answer.
I have a scientific answer
Thank
for
you.
this, but I'll let maybe someone should answer from the.
So how about interest of time? Actually, we're going to a next topic talking about some of that. So if you just postpone the comments on that for a bit, that will be. Thank you. I appreciate it. Thank you. So let's go to the next topic on measurement data sets. So we touched a bit earlier about raw measurement data versus clean out data. Okay, so the question, does cleaning or processing raw measurement data can actually result in an information loss? And would it better to preserve the raw measurement data in case hidden features can be uncovered later on? And I think Franco, we already probably provided half of the answer already. Okay, anyway, so Max, you want to comment on that? Yes, thanks.
Yeah, I'll just repeat what Frank said. Really, he had a good point about the merits of keeping all the intermittent sort of processing steps. I'll just say that if your company or organization has something set up, some version control for the software, that's really important. But if you're just going out taking measurements and then doing post-processing, the one thing that I've learned that's really valuable is you've got all your processing steps, and each one has a bit of software that goes with it. If you go out and take 10 measurements and you process the first measurement set, you should save off each of those processing steps with that measurement data, because you're definitely going to run into some edge cases with measurement data 3, and you're going to change something in step 4, And so now you have a different version and you don't know how you processed measurement 1. And so that's all I'll say here. Keep your code, a copy of your code with the measurement data. It saves a lot of headaches.
I can comment really quick on that. I go much farther. We scientifically, we have to revision control our workflows. And if you're building accurate models and going to treat them scientifically, they need to be both calibrated as well as validated, as well as you need to actually have workflows. Another advantage of lower level data is you can reprocess it into the next workflow. We've historically done some stuff where we preserved IQ. I have a radar system, for example, at Haystack. I've got very narrow band IQ data going back to 2001. Okay, off our system. We just keep it because it was narrow bandwidth enough. We invented algorithms later both to clean up the data and to process it that didn't exist when we took the data, but we were able to reprocess everything from scratch because we had the very lowest level data available. Now, you can't do that for everything at every level, but it's very important to that. The other thing I'll say is everything in data reduction is filtering, right, when you get down to it. It's trying to pull and extract using filters what you want from an environment. And different applications have different filter stacks or different convolutions of filters. And you need to be able to, you can't go back, through certain processing steps. They're non-invertible. And so you can often end up in a situation where you really, really can't reduce the data for any other application because you destroyed the actual information content. That's just inherent in data reduction at some level.
Okay.
I can add.
Yeah, Julius?
Yeah, we talk about consensus. Within our organization, even internally, we have to have consensus because the propagation modeling is handled at the national level. Then we deliver the calibrated propagation models to the market. So with that, you have reports for every single thing to get the raw data, the process data, the model assignment polygons, the reports, the signature of the model that is calibrated. Then it goes to them. Then they look, and at times they have to go through and check before, and even go to the extent of even validating on their own, despite the fact that it's accompanied by the data that was used for validation and the validation reports. Yeah, so it's critical that all the data is kept.
Okay. We'll go back to this one. Thank you. This is quite I have one more question under the data sets. So we mentioned earlier the variety of measurement data available, people collect it and they share it, is not always identically collected. There are different procedures and approaches how to do it. So the question is, if for someone working on a calibration or development model, if separate measurement data sets are available, and given that each of those data sets will have its own particularities, we can call it this technical DNA, how it is being set up. Is it possible to be used together as an ensemble in order to combine them in a more comprehensive measurement? Max? You want to?
Yeah, if I'm going to go search online for a data set that I need for some problem we're working on, it's really nice if that data set is in plain text. And so if it's IQ, you can't really do that. But if it's in DB, there's no reason to store that as an int. Whatever savings you're going to have or float, whatever savings and space you're going to have is just not worth it. And so I have had this conversation with colleagues. It's just like, put your stuff in plain text. That way I can download it and look at it in a JSON or a CSV. As far as I know, every data set is a snowflake. They're all unique and beautiful in their own ways. And it takes, at least as far as I know right now, a human to look at that data set and figure out, okay, what did they call their path loss? What did they calculate free space for me? That kind of thing. So
I'll disagree slightly about the binary. Yeah. So we built a lot of systems actually years ago that used XML, for example, for things. And what we found is we hit data rates pretty quickly where we couldn't actually, the parsing overhead was the dominant processing overhead. So as you push up data rates, as you have ubiquitous sensors, as you have millions of sensors contributing, the cost associated with non-binary approaches becomes very significant. And if you're starting to do things on very large modeling scales in a simulative manner, the supercomputer time associated with that cost becomes absolutely prohibitive. You end up spending so much money parsing the data that you get murdered. For some things like general availability, you want to, for the end user, have the ability to transparently translate from a binary storage internal manipulation format, a data stream format, into a end user format of text or JSON, or what that or directly into Python or MATLAB or whatever they're using. So that's really, really, really critical, I think, to have the ability to format and give a good user experience to the person analyzing the data, running a model, running their Jupyter notebook or whatever it is. But then to step back and go, well, at scale, you can't do that. And there's really good economic reasons once you push it up to large scales where that's not such a great idea. My different perspective.
No, it's good.
So going back to something that Julius said earlier. So if the technical details of the collection of a data set are critically important, okay, they're always in order to understand and use it later on. You mentioned that within AT&T, you fully documented, you have full version control available for everyone to make the good use of it. And okay, so could such technical information be abstracting some kind of metadata? Okay, and could that metadata be possibly standardized? I'm talking if we're possibly sharing this data among the community. Would that be something beneficial that can help everyone in order to share and make better use of this? Barak, you want to comment?
Yeah, I think it'll be another panel to come to consensus, perhaps, what that metadata should be. I think, some of the details of the measurement, they need to be preserved, right? In order for an end user to really understand the uncertainties, assumptions, and make decisions based on a particular data set, they need to know the technical setup and what was used in there. So I think if we do some sort of a standardization, there could be a risk of information loss in there that otherwise would be there. Trying to reduce the data and trying to fit to a particular size and shape, there could be a risk for it. It could perhaps be done if it really paves the way into more sharing and being able to use different collections of data together. It's perhaps a requirement to standardize in order to get them into the same shape and form. But I think that also means that there will be some loss of information along the process.
Okay.
I can comment briefly. Standards help. They drive things. I will say it's more important to be extensible. It's more important to be self-documenting. It's more important to have good physical units. It's more important to have variances. Ultimately, data that doesn't have variances, you have to analyze the data that's incoming in order to generate a empirical variance. So wherever you can, if you can actually nail down the accuracy, this gets to the time question that actually was there before. I'll give you my answer from the scientific community. We align with PPS to the UTC epoch, and then we do everything in samples since 1970. So we absolutely align the samples at the IQ level, and then everything else flows through from that to be aligned to the resolution of the data timestamps, which get reduced, of course, if you do averaging and so forth. So there is no time but UTC.
Okay, thank you. So I'm mindful of the time. So before we go to the next topic on geodata, any questions? Yeah, thank you.
Yep. Yes, we do. We've got a couple questions online. So Matthew Chatevers from the Communications Research Center, apologies for pronunciation, said, how should one deal with measured data points that aren't capturing any signal? How do you integrate measurement below the noise floor into your building model?
I'll maybe take that. And first of all, I think if you look at the raw measurements, there's always a measurement. It may be noise, but there is a value attached to it. And this is, of course, in the case of CW. So what is typically done is to apply a filter in order to sort of isolate the points or measurement samples that are close to the noise floor with with perhaps good reason, because you don't know if you're measuring the noise or the signal itself. That's very, when you get too close to the signal, the noise floor. So the challenge with that is it actually introduces a very large bias to the data, because you are keeping the high signal
Only
levels.
the good coverage points.
Yeah,
Is that the
you
request?
keep the good coverage points and you discard the low, that the low measurement. So it creates a bias, and I mean, we in our modeling we actually patented a technique that mitigates this. We call the dynamic range compensation. It's a mitigation technique that we see this all the time. It's and it's there not just with the CW measurements, but in different network measurements as well. You're dynamic limited, and you see this phenomena quite a bit. But in the raw data, you always see some sort of data.
All right, second question from Matthew Mandel, senior scientist at RKF Engineering Solutions. In recent years, AI and machine learning have become buzzwords in the context of using measured data to develop path loss clutter models. What exactly is the difference between AI and machine learning and using data to calibrate a model? Perhaps yesterday's panel on modeling can comment, and I believe that's referring to Billy's panel.
Maybe I'll try. Frank,
I mean, if you want a general,
go ahead, Frank. Yes.
A general differentiation. I mean, we have models. We take data, we assimilate the data into models or invert or fit. That's all straightforward linear modeling often, or semi-linear modeling. You often take a problem and try to reduce it to a linear model. The AI models that are we're thinking of as large language models or different types of modeling using neural networks are specific nonlinear modeling methods that they often can adapt to kind of a wider range of things than a linear model. They often are more obtuse about what's going on. Making transparent AI models is actually very challenging. I think that this is we're going to see a lot of AI no matter what, because there's a lot of money going into it and buzzwords, as you said. At the end of the day, the question is whether the model you're creating is predictive of reality or not. Okay. And nonlinear models have some advantages in edge cases, in non-Gaussian distributions, in things that are evolving, maybe in timescales that your linear model isn't going to be able to adapt to. So there's places it's going to come up. I do think, getting back to the prior question actually about, well, say you're taking a time frequency spectrogram off a sensor and you're walking into a building, and as a human being, you can look at that and watch the signal level fall off and go, oh, wow, I'm still seeing the sky and I have no longer seeing the cell phone tower. Well, an AI system can probably do something like that, looking at the large frequency, time frequency waterfall, whereas just a simple instantaneous model could not. An instantaneous model would say, am I seeing the sky, right, when the signal is gone, which is a whole nother question. And so, if you go and, you can ask problems, like I asked some simple problems of the SpectrumX AI ML folks for some of our measurement platforms, which is, am I seeing the sky? That was the simplest one. And, is the software radio working is another good one. Well, no, you can plug these things in, and the first order thing that you get is a lot of signals and noise and interference and other stuff. And it could be that none of it has anything to do with what you're wanting to measure. So, so you have to be careful with this and what in detail is being intended by an AI ML, for example. We're just seeing radio and AI ML start to happen at the edges, and I'm sure it's going to be the next big thing once imaging is done. So
it's a very big topic. We can take it offline if more questions.
The whole panel.
Yeah. All right. So let's go into the geodata, and now actually we're going to talk about the tolerances and precisions. So GIS data is time dependent. How do we account for time discrepancies, for example, between RF measurements, data captures, and the GIS data capture? So you collect the RF measurements at a specific time. Your geospatial data set was generated not at the same time. Okay, there will be differences. How do we deal with that?
Did you want me? Who did you want?
Yeah, sorry.
I think you wanted me to talk about this a little bit.
Yeah.
So temporal alignment is fundamental, and especially down at very fine levels if you want to do things like, we do like multi-static radar and stuff. And when you do that, for example, you need very high precision alignment of data. It's worse than just the instruments themselves having to be locked and oscillators locked, et cetera, because signal processing paths create delays. And if, for example, you don't know what the signal processing path is, now there's some arbitrary offset in data. One of the ways to handle this is to constrain what you'd use to actually have those qualities or measure it. So for example, when we calibrate our radar system, what do? We actually measure the impulse response, the bandpass response of the filters. We also do what we call a zero range measurement. We measure the range delay all the way from the transmission source to the antenna phase center, back to the signal processing, and through the software signal processing.
A very comprehensive calibration.
Yes, you have to calibrate it out. I've seen other communities like the oceanographers. They were building a wonderful data combination systems, floats, buoys, submersibles, every kind of thing in the world. And then they were trying to relate, well, we saw something in one sensor to another sensor in some spatial position. And what really killed them, and it ultimately caused a complete rethink, was that none of the clocks lined up. And like things that they put underwater, the oscillators drifted around and they'd be good to a minute, but that was it. And so when you wanted to do something saying, well, we saw this wave here and then there, and it propagated very rapidly, you couldn't do it because there was no way to actually register the data. So I think that there's an aspect of that. There's an aspect of understanding and propagating the errors in your time base in systems. But the real hard part with this, and why you also have to revision control signal processing chains, is there are data-driven latencies through systems that you really have to account for. And a lot of systems like the cell phone networks try to minimize these latencies just so that the user experience is good. And but understanding those things systematically in the measurement systems is hard, and it's something that you calibrate out.
Thank you. At higher frequencies, and we're moving towards that. Right now, the focus was on mid-band for the last few years, now going 7, 8, and higher. And actually, I'm mixed up. I think we talked about this in the first day or the second day of the conference. How I think it was the panel in the second afternoon. The risk of under or overestimating the path loss when using clutter, where you might have line of sight. Okay, but the clutter being statistically, sometimes in specific cases we'd miss that. So at high frequencies, line of sight or non-line of sight becomes quite crucial. How does one account for location variability in building location and in measurements location? So the GIS data says that we have are not perfect, okay? The OpenStreetMap or whatever database out there that tells you have a building right here, well, okay, there's always tolerances to that. The GPS measurements that we take, they're not totally accurate. How do we deal with that? How is that being, how strong can that impact the measurement, okay? And how do we minimize it? Barak, you want to comment on that?
Yeah, so I think in our approach, first and foremost, we try to be accurate, right? We try to be as accurate as we can. And I think in the geodata, in the GIS layers, in terrain and clutter layers, or where the buildings are, specifically what you asked for, there is products that are generated from, imagery that's, less than 30 centimeter in resolution. So it can be very accurate. That could be, sub-meter accuracies at the XY sort of location of the building. As far as the data collection and field measurements go, we also achieve sub-meter accuracies in the GPS locations, even in dense urban areas, through use of dead reckoning system, IMU, wheel sensors, differential GPS. Using all that equipment, we do achieve sub-meter accuracies there. The challenge is that the GIS, I think, community is having more. I mean, my point is, as far as for the use case that we're doing, and we're trying to predict, 1 meter, 2 meter resolution. So being sub-meter inaccuracy of the location is sufficient for us. So, it meets the demand. The products that we deal with today generally meet the demand in the XY axis. As far as the Z axis goes, that's a bit more of a challenge. They have different products depending on how close the measurements were taking close to the ground. You have the low altitude flights, you have high altitude flights, you have low orbit satellite measurements that generate some of these height layers. On top of that, they have to subtract that from terrain layers. There's some variability in there. Maybe they can still achieve, I think, plus minus 1-2 dB, 1-2 meter accuracy from the sea level. So I think that's where the challenge is coming from. And you mentioned OpenStreetMaps. Yeah, I don't know what's the advertised accuracy of that. I don't know if there is one. So I think they have to be accounted as uncertainties in the measurement and as variances in the measurements, and not measurements but predictions.
Any questions from the audience before going to the next topic? All right, so sharing measurements data. Okay, so there isn't a real incentive for many organizations to share their data. And given it is quite expensive, sometimes quite proprietary, it could be confidential. What could we do as a community in order to create incentives for organizations and folks to share their measurement data? Julius, would you like to comment on that?
Yeah.
Obviously, you have in AT&T a lot of measurement data. I like to get some of that.
Yeah. To start with, I don't think there's any doubt saying sharing data with the community would benefit everyone. But again, we've been talking about good quality data, right? Because it's good quality data that needs to be shared. Because if one were to go and share data that is not good quality, it may really do harm instead. But even with that in mind, you see the situation where I'm going to break this down into maybe about 3 types of measurement data. We've talked about the CW data that is used for model calibration, which really, if you look, say in our case, nationwide, it's really, really expensive to collect. So now what happens is, typically, those that have gone through the same process will say, what is it for me sharing this data?
Maybe you can get more spectrum.
Right, which goes towards the incentive, right, that you're talking about. Because if it's just sharing for the purpose of sharing, the likelihood is, the probability of sharing is slightly low. And again, with the CW data, it's got a shelf life. Because one of the things is, like we mentioned, clutter changes regularly, so as the validity of the CW drives. So you spend all these tens of millions of dollars to calibrate models, which needs to be repeated maybe every few years. Then you see that you have to share. Maybe somebody was just waiting to get the shared data and not spend. So that type of thought process. Then the other thing is, if we go to the other end of, say, measurement data, we can have measurement data that is not for model calibration, but to fit into a process that helps with some type of analysis, be it for interference analysis or whatever. So that may be network counters. And as a matter of fact, Niti touched on that yesterday, where some part of, say, measurement data from the network from counters are really being shared. But again, that needs to be shared to the right individuals and in a way that does not disclose certain characteristics of the network. So then you are looking at a situation where it's limited sharing, maybe under NDA or whatever the case may be. Then the other aspect of measurement data may be the UE data, crowdsourced data, or whatever that comes from the network. That in itself includes its own privacy aspects and all the like, which would make it maybe not easily shareable. So you start having all this complexity. So now the question now becomes, let's start with, say, the CW measurement data. As an incentive, can there be a way of cost sharing where the community comes together, like use cases, and say, okay, if say this group of users with a common type of use case would have the same need for the same type of measured data, measurement data to utilize, can they be cost sharing in such a way that now it's cheaper for everyone than doing nationwide on their own, but at the same time they get their end goals. That way, then it becomes easier to have that type of discussion. If it is in the case of the counters, yeah, that's stuff in the network. That is not as expensive as the CW data, but then, despite the fact that it can be collected, it now becomes a part of really seeing why would there be an advantage, because I may be able to share that data if at the end of the day, it facilitates me doing certain things with spectrum that I may have acquired and all the like. So that would be the type of thought process. So at the end of the day, what happens is really, it needs to start with what is it that the owner of the data is going to get in return as a result of sharing. Yeah.
So as a follow-up on that, could you comment? So when we talk about, I don't know, a use case or an area of interest for sharing or for interference management that perhaps is for the public good, do you see perhaps a role for the government agency to step and maybe take the lead in funding or conducting some of these measurements, like NTIA, CRC were part of the federal government. I think we have people from Ofcom here. So
actually, I can add to that.
Yeah,
Yeah. So let's take the example that where you have, say, maybe a service operator like AT&T, where they're doing a lot of work to really meet their day-to-day business as usual. Then at the same time, you have like some of the type of analysis that may not be regular business as usual, but for some type of analysis that is unique.
Policy development.
Right? So let's take, for example, that even if they were to fund those studies to carry out measurement drives that are specific to that specific use case, then we are still left with the other use case where the operator will still need to carry out their own analysis. So now, but at the end of the day, what we cannot run away from is measurement data of one form or the other is needed to validate whatever type of model or develop models.
So, Burak, your organization is involved in this is what you do for a living, right? Doing measurement data. Any comments on this as well? So, yeah.
Yeah, I mean, I think certainly a government funding would help, bring data across to everyone. I think there would be challenges on how to keep it fair, because you have frequencies that they have different ownerships. You have geographies that have different, license assignments. Keeping it fair for everyone, could be a question. Like, is who wins the most, who wins the least? If in the case of a collection like that, could be, but it can certainly be something that can be done.
Any questions?
I'll just say real quick that open data are key to scientific reproducibility. And on the science side, everything is now in like the journals being mandated to go to do that. And of course, it's coming also kind of from high on. So there's a policy aspect to this.
Of course.
And your fairness aspect is also a key thing. It's not fair to go to AT&T and say, hey, you please share, we're good. You share your data with everybody and your competitors don't have to. That's the situation you most want to avoid almost. So I think that there's some of this is that the paradigm we have structurally, the rights, the policy aspects of this come into what is fair for everyone. And then also in the privacy aspect is certain data we don't want shared or for defense. There's things that you don't want necessarily public.
Yeah. Thank you.
So my question sort of like on the calibration of different data sets. And how could we possibly calibrate between the setup of each of you produce a different data product, but you go to the same exact environment and you measure all your different ways. And at the end of the day, you produce data products. And if you compared those, probably going to have 4 different answers. So how could we calibrate against a known good? And is there a need for like a reference setup or a reference environment that is sort of a proving ground for a measurement approach to go to and validate that, hey, I've gone to this environment, I've produced values using my setup that are consistent against a known good?
I think in our practice, I don't know if I would. I mean, you do get 4 different answers, perhaps, but I actually don't agree that it will be 4 wildly different answers, for instance. So one of the common practices that we do, we go out, collect CW measurements, we create propagation models with that. And again, the propagation models, the goal is to model the path loss. We're not trying to model the signal levels, right? We're trying to model the path loss. And then that's used in the software to predict what the signal will be. And a lot of times, part of the validation of the models that we provide to our customers is to go ahead and collect, compare that against network measurements, which are typically collected with scanners and completely different setup. The signal is coming from the network, completely different, origin for the signal. It can have different receivers that are attached to the system or so different sort of technical DNA for the test system. And yes, we do expect some uncertainties, but there is a very good agreement between the models and how that is created with the CW measurements to a validation that's being done with a completely different setup.
Just 1 second. Jeremy, I think we're out of time. I think we started behind schedule. Do we have a few more minutes? Or
I think we have a gracious crowd. I think you have another question that we can a couple more minutes.
I have a comment on the last one real quick. You really ought to get n times n-1/2 different estimates. And so you should form a covariance matrix of all the estimates and then look at it. And if the measurements have good error bars on them, you should be able to tell that they're accurate to within or without of the error bars, at which point you either have outliers that are out of the ensemble, or you have things that all fit within the error bars and are therefore the same number effectively.
And from an engineering perspective, I think we were discussing this earlier. If the measured data is collected systematically, correctly, and fully documented, all the parameters of the testing environment, equipment uncertainties, and all that, then the user can extract the core data of the propagation itself, and that should be consistent between different measurements. Thank you.
All right, one last question for, I'm Stéphane Gagnon from the Communications Research Center in Canada. So for 5G and 6G, we hear more and more about sensing being part of perhaps the equipment that you deploy in the future. Maybe the question is for Julius and others. Do you feel that sharing that sensing information perhaps should be done or asked by the government for the greater good of everyone? And when I say the greater good is to maximize the use of spectrum for basically all citizens of your pick your country.
Actually, if it is beneficial to everyone and depending on what surrounds the ask, then I think as long as it is beneficial to everyone, maybe that's an approach.
But I do think there's a difficulty here in making sure you create equal market. So for example, AT&T is not really just competing with other cell phone providers. You're competing with potentially space to ground, Wi-Fi, ubiquitous long-range Wi-Fi, new applications that are going to come along that might try to displace you. And so there's a challenge there in that being fair to all parties isn't as simple as being fair to all cell phone companies. And so I think really thinking about that in the context of policy is something that needs a lot more exploration.
Yeah, and that's one of the reasons why
asking is different from accepting.
Yeah.
Right.
Okay. Thank you. I think if there is any other questions, maybe we can take one more. I think we'll skip the last topic, use of directive antennas, unless there's a great deal of interest. If someone is really wants to talk about that, maybe because we run out of time, really. If there's interest in it, we can discuss offline. Okay, we're still up. All right. Thank you very much, everyone. Okay, I think we had a very interesting discussion. Thank you.
Thank you to our panelists. And we will break now for lunch, and we'll get right to it. And we will reconvene at, I believe, 1:45 in about 85 minutes. Thank you.